So it's really a great pleasure and honor to introduce Professor Mahadev Satyanarayana.
Very good.
Right? Okay,
Fantastic.
he's just known as Satya. So
right.
That's what we call him. He's a professor at Carnegie Mellon University, and over a long career, he's pioneered many advances in distributed computing, mobile computing, and pervasive systems. Years ago, he introduced ideas in scalable file caching and ACL-based security that made its way into IBM's AFS file system. He's contributed lots of ideas on disconnected operations, cache exchange modes, layering VMs on distributed storage. And many of these things have worked their ways into well-known products that we know, such as Dropbox and Microsoft's Word and Outlook. He was a visionary in the field of cloudlets, being the first to imagine mobile devices offloading resource-intensive computation. Is a fellow of the ACM and the IEEE, the founding editor of IEEE's Pervasive Computing magazine, and I could go on and on. But I'm going to stop there and just say we're really very happy to have you, and he's going to talk to us today about some interesting ideas in the intersection of privacy, cloudlets, and computer vision.
Great. Thank you very much, Nina. Everyone can hear me clearly? Is there some way to get an act? Okay. I didn't quite know how you get a remote act on this.
I saw a thumbs up over there.
All right, great, fantastic. That's exactly the end-to-end acknowledgement I need. So my talk today really is in 3 parts. First, I want to share with you my thoughts on the cloudlet concept and its relevance to video, which happens to be especially interesting. Second, I want to talk about privacy in the Internet of Things, which I think is of interest to a number of you. And then it turns out that cloudlets have a unique role to play at the intersection of Internet of Things, video, and scalable deployments. So this is quite interesting there. And in particular, it has a role to play in what I call denaturing data to make it safe for releasing publicly or semi-publicly. And I will explain how we have successfully implemented denaturing of live video, streaming video at full frame rate, including face recognition, so that you can selectively mask people's faces in the whole thing, okay? So assuming that I'm able to get through all of it, I'll get that far. I'm happy to answer questions as we go, or at the end also, okay? Whatever works best for you. So I'm at Google. Obviously, you guys know what a data center is. In fact, I think if I'm not mistaken, this is a picture of a Google data center. So interestingly, there are other kinds of data centers, and here are some pictures of some things you can actually buy today. Those are commercial products of different sizes. They're mini data centers in a box. That's a data center over there on the left, right next to a bunch of cars that are parked there. You can find them with wheels, et cetera, et cetera. And there's even one that Nokia introduced in 2013 that can sit right at a base station, okay? So this general idea of providing computation at the edge of the internet is kind of there, but it hasn't been highlighted in a big way other than a few people like my research and a couple of other researchers who have been working in this space. But you have things like this. Most of these are typically used as private clouds. So for example, if I have some kind of industrial setting and you want a self-contained cloud for that setting, you might use something like that thing over there. If I have a disaster recovery situation, you might truck in one of those things and set up a private cloud for the duration of the recovery process. So what is different between any one of these and a cloudlet? So here's the way to think about this, that it's a small data center at the edge of the internet. Up to this point, it's the same as what I just described. Use standard cloud computing technology, virtual machines, isolation, safety, all those other things. So anything that is important enough to use in the Google Cloud has a good place also at the edge, okay, in terms of safety and things of those kinds. But logically, I think of them as subordinate to the cloud. Think of it as a second-class data center. Let me ask, what does it mean to be a second-class data center? Basically, it means if I blow up one of these, no one sheds any tears. Okay? In other words, the state in a cloudlet is fundamentally soft state. It's cache copies of various things, or it might be locally captured data, which I have distilled and the most important parts have been shipped off elsewhere. Maybe I have some amount of full fidelity data buffered for a certain period of time. If you blow up the cloudlet, you lose that. But other than that, there's nothing very important that you would use. And so it is that aspect that makes it even conceivable to deploy something like this and to manage it. Because if you really had hard state at the edge of the internet, it would be an unmanageable deployment. So from the viewpoint of mobile devices, like smartphones, Google Glass devices, any of these things, as well as sensors, of course, these devices already have lots of sensors. There are two things that make a cloudlet special. First, it's plugged into the wall, so you don't depend on battery power. That's very important. Second, because nobody's carrying it, nobody's wearing it, you don't have to worry about its weight, its size, how much heat it's dissipating, all the things that make mobile hardware design considerably more complex, okay? Just those two benefits alone make a big difference in how you can leverage cloudlets, combine them with Wi-Fi or LTE wireless to a mobile device, and the two together can accomplish a lot that would be very difficult to do by itself, okay? And behind this thing here, basically the point that is made there is that it's a catalyst and enabler for interesting new applications, one of which is the kind of thing that I'm going to talk about today. So here's a takeaway kind of slide. There are 4 reasons why cloudlets are valuable, okay? One reason is highly responsive cloud services. No matter how hard you work, from Pittsburgh, the Google Cloud, if it's located somewhere around here, is typically of the order of 70-ish, 80-ish milliseconds. Okay, it should be only 30 milliseconds, but it's never that low. There are many applications, augmented reality, variants of augmented reality, things of that kind, where much tighter latencies and also tighter control of the jitter is needed. And every hop, by definition, introduces queuing delay. You simply cannot control it. At the end of the day, you're going to have increasing jitter as the number of hops increases. Now, if you're deploying Google Fiber everywhere, maybe this doesn't matter, but to the extent you deploy in public infrastructure, you do care about end-to-end latency and jitter, and this is one of the things that cloudlets give you because they're physically proximate. Now, you may have heard of 5G in industry. You know, a millisecond RF latency, maybe even sub-millisecond. Once you talk about that kind of thing, it's pointless to even have it unless you have cloudlets. Because what's the point in accelerating the first hop, and then you're going to spend 70 milliseconds to get to something useful before any work can be done. So the existence of cloudlets actually makes low latency wireless technologies interesting and valuable. So the second thing, independent of latency, is bandwidth. It's very easy to just think about this. Imagine if every one of you were wearing Google Glass and capturing video continuously, or a GoPro capturing continuously, or I had a whole bunch of video cameras from automobiles in a certain region. Shipping them all to the cloud, if you just do the back of the envelope calculations at scale, is really prohibitively expensive, okay? Assuming you're doing this continuously, because there's no nighttime when you can say, I can do statistical multiplexing, any of those things. You're talking about continuous streaming. So if you wanted to do any kind of analytics continuously, you're much better off doing it on a cloudlet and then only shipping the extracted information, which is usually much, much lower bandwidth. A different value of cloudlets has to do with the Internet of Things and privacy. So we all have been using network firewalls for a long time. And the concept of a network firewall is a piece of equipment that keeps bad stuff out, put very simply. The way to think about a cloudlet is that it keeps sensitive stuff in. Right? So it's a firewall in the reverse direction in the Internet of Things. So if I have an enterprise or a home or some trust zone, okay, under someone's control, there's a whole bunch of IoT devices. Viewing a local cloudlet as the landing point, the first point of contact for all the data, is very helpful, because that becomes a choke point at which you can enforce any kind of denaturing, any kind of redaction, any withholding of data selectively, et cetera, et cetera, et cetera. The last value of cloudlets has to do with failures. So you're all aware, not that long ago, 2 weeks ago, I think there was this big denial of service attack on a number of service providers. Depending on what Putin and his friends are doing, there are going to be more, right? I mean, this is becoming an unpleasant but real fact of life, okay? And of course, there are use cases like the military, disaster recovery, et cetera, where the network is really cut. So it's not just denial of service attack, but physical damage to the infrastructure. You can think of a cloudlet as a temporary fallback node on which to run fallback versions of cloud services. It might only be limited to your home, for example, if it's a fallback service of cloud. Now, this won't happen accidentally. You have to build your service in such a way that it is possible to have a fallback version elsewhere. We have successfully shown it. Nina mentioned disconnected operation. So that's an example in the context of file services, how you can do it. But you can extend this idea. You can imagine a Google Maps, including updates, being done in this way, so that if there were transient periods of unavailability of the cloud, the user and the users who are using the cloudlet are unaware. It's completely transparent to them. So this is why cloudlets are interesting. And we could spend hours on each one of these. In this talk, I'm actually only going to touch upon two aspects. The use of cloudlets in the context of video, because it offers scalability, and denaturing that video in the context of privacy, okay? So let's talk about video. So there was a report about 3 years ago from the National Science Foundation, and I love this quote that comes from there. It'll soon be possible to find a camera in every human body, in every room, on every street, and in every vehicle, okay? Obviously, it's stretching out into the future a little bit, but it's not that far-fetched. Here's a number that's really quite stunning. That according to the Daily Telegraph, which is a British newspaper, in 2013, there was one surveillance video camera in the United Kingdom for every 11 people. Okay? So, it's not quite there, but it's headed there. Now, many IoT things are video cameras. Nest has a video camera now, right? The thing about video is they're easily integrated. They're small. You can put them on the body. You can put them on a dashboard. Yeah, they're quite easy. The other thing about video is that it allows passive real-world sensing. Most of the kinds of sensing, you have to give the person the sensor. Maybe it's a smartphone or some other wearable device. They have to wear it. Or you have to install some app. The thing about video-based sensing is it's completely passive. As long as you're in the field of view, you are visible. Now, you have to do a lot of analytics on it to extract useful information about what you're doing. And there might be significant ambiguity in that interpretation. But it has huge value in terms of the passive aspect and the ease of deployment. The price you pay is, of course, that there are high data rates and high bandwidth demands, so the scalability issues I mentioned come along with it. And, of course, privacy is a big, big issue. So in the context of cloudlets, the general idea is that you would do the video analytics. Basically, think of a cloudlet as a local IoT hub. Okay? And selectively, whatever you extract, what information you extract for it could be propagated more widely to a cloud-based IoT hub. And this general picture has two advantages. One, from a bandwidth point of view, is certainly more scalable. And secondly, from a privacy control point of view, this cloudlet is a physical point of control as well as a logical point of control for data that is being analyzed in there. Okay, so think of this, if you look at it, it kind of looks like a CDN. And so one way to think about this is it's a reverse CDN for video data. So what are the kinds of ways in which video might be useful? And obviously this is speculative here because these applications haven't been built yet, but think about, I walked into this room, I recognized people, I met Nina, I instantly recognized her, right? I mean, so in the physical world, face recognition, person recognition, dog recognition, right, it's fast, it's quick. You can think of it as biometric authentication if you want, but that's what we use, and we do it all the time. So it suggests that perhaps having it as one form, one capability in the Internet of Things world is quite useful because you can use it to modulate the interactions, you can make it part of context. So if you have a context-sensitive system, that's part of it. So that's one line of thinking as to why video might be useful. A completely different line of thinking has to do with societal benefits. So, very often, if I can point a camera at a public space, like a checkout area of a grocery store or shopping mall or something, and see long lines, and I'm able to estimate that very fast, it's a valuable piece of information for somebody to make sure people aren't upset. If I could do emotion recognition and look at the expressions of people's faces, that is an additional, you don't need to know who they are, but upset person, upset person, upset person, happy person is an example of an anonymized, valuable piece of information that could be used as an output. So these are some simple examples, but think of public safety. We get ice in Pittsburgh, so knowing exactly where to put the salt is always a big challenge. You'd like to try to minimize its use because it's bad for the environment. So being precise about it helps. So if I could, with a video camera, see where people are slipping and nearly falling, it's a simple way, trivial way. Another example is road intersections with many near misses, right? Ideally, you'd like to catch it and put a traffic sign or a traffic light before there are too many accidents. And the near misses are not typically reported. So counterterrorism, law enforcement, et cetera, et cetera, et cetera. So in general, this general concept of video analytics as a tool, possibly as a cloud-based service or cloudlet-based service, depending on how you want to structure the details, appears to me to be a very powerful general capability, okay? And the other thing about video is that once you have deployed a camera or a set of cameras with adequate resolution, frame rate, et cetera, you can increase the sophistication level of the algorithms and extract more information from the same pixels. That's usually not easy with other kind of sensors because they're not very rich sensors. Okay, so what do we do about video and privacy? The essential idea is that if I could reduce the fidelity, content-based reduction of fidelity of video, the hypothesis is people are likely to be willing to accept that in return for some of the benefits mentioned in the previous slide. In other words, if you told people, look, we'll reduce the fidelity of the video in the following ways. We'll blur faces, any children that look below some age will completely blur, etc. Some societally acceptable or community acceptable policies can be used in this. Now, exactly what is going to work and what is not is going to be very different in different use cases. So there's not going to be one approach that fits all. So my approach here is to say, it's a classic policy and mechanism separation. Can we come up with a mechanism that is rich enough and capable enough that there's a plausible range of policies you could express with it and enforce. Okay, and if you can do that, then, and do it scalably, then you have something that is a useful tool. You'd still need to figure out and somehow get buy-in from communities on the acceptable policies, but you have something workable to start from. So that's, most of my focus is on mechanism with reference to policy only to the extent that it might explain why you need some particular function or capability in the mechanism. So here's some examples of denaturing. So, children, you blur the faces, right? Here is a couple, you blur the faces. Now notice, this is a more aggressively denatured version. I even removed the location cue. Okay? So this does not require face recognition. It only requires face detection. This one is selective face blurring. Say maybe this person is a famous actress or something, a political figure, therefore we don't need to worry about privacy, but this person doesn't fall into that category. So you've chosen to have a policy here that says it's okay to show one person's face, but not the other. That requires face recognition. So if you think about it, I can give you a blank video that has perfect privacy, but is useless. The other extreme is the original video, full fidelity, full resolution. You've lost nothing, but obviously the exposure of privacy is at the highest. The real question is, between those two extremes, where do you draw the line? And that is really a policy question. Okay. All right. So, come on. So a couple of points about what we have learned about face recognition in the context of IoT, right? Google has a big team working on these kinds of things. Facebook has another big team, right? You guys have huge databases of faces from the various social media products like Facebook social media product, Google+, and they're labeled, right? It's fantastic. So with those, and so the people who would have the best, in fact, are the passport people, right? For the entire population of the country, they have faces and labeled information about those people. So typically, training is thought of as a kind of batch operation. It might take place overnight. And today, most people view face recognition as a kind of a big data problem, right? There are millions of people, and I have this face. Who is it? Right? That's the kind of question people are interested in. But in the mobile/IoT world, the flavor of use case is actually rather different. Think about the following. You get on a bus or a metro or something, and there are a few people in there. Within just a few seconds, you have learned their faces well enough for the duration of the 10 or 15 minutes. You'll recognize, you don't need to, you know that this is the person you saw sitting in the other seat. And later in the day, if you see this person somewhere else, you may not know where you saw them, but you will remember that I know this person, just like I knew Pulkit, right? I didn't quite remember where I knew you from. So interesting point here. Notice how fast the learning occurred, right? It's not an overnight batch operation. It's live, okay? So learning in short periods of time is valuable. And I don't need the full identity of the person. So for example, think of a home situation. I have mom, dad, a couple of kids. I know their faces. Let's say we've trained them because in a home environment it's useful to know the preferences. We have 2 guests for dinner. I've never seen them before. I'm not going to see them again. They're visitors. But for the 3 hours or whatever they spend in my home, if I could learn their faces in a few seconds, then I now have, for the duration of their stay there, a useful way to disambiguate between different individuals. Okay? You can think of many, many other use cases of this kind, passengers, transient interactions, etc. So Key point here is that learning new faces has to be fast. This is, and you have to learn them individually. It's not one of these where you give you a million faces, learn them all, and then give you a quiz the next day on which face is this. All right, so now let me switch to the concept of privacy mediators, which is work I did with Nina in the context of Internet of Things, okay? So I don't need to tell all of you that IoT is big, right? When you guys started it, $2.4 billion is the number I remember from the purchase of Nest a few years ago. Cisco created a IoT business unit. Intel did the same last year. And I am told, I mean, I don't work for Intel, but I'm told by hearsay that this is already profitable. That's stunning to me. I guess they make specialized chips and things of that kind for the IoT business. Cisco last year, about a year ago, created the Fog Computing Consortiums, similar to the Cloudlet concept, but it's very Cisco-centric, as you would imagine. So no question, IoT is big. Here's a stunning number. According to these guys, okay, IDC analysts, though frankly, after last night, I have a lot of skepticism about analysts. They claim that the IoT market could hit 8.9 trillion by 2020. Okay, that's a stunning number. Just for reference, the entire G20 internet economy, which includes Google, Amazon, people like Intel, Cisco, the whole thing, all of the infrastructure, all of the services, everything of the G20 countries was $4 trillion. So the claim is the IoT market just by itself is going to be more than twice that. That's a huge number. However, while all this is very exciting, there's growing evidence that IoT is running into trouble. And is running into trouble specifically in the context or on the basis of privacy. So here's some quotes. This is from 2015, right? So consumers are highly anxious about companies sharing their data. And this is very interesting. While older generations show higher concern, strong discomfort with the use and sale of connected device data is pervasive across all age groups. So this is not just old fogies, who haven't gotten on with the times, according to these, and I have the full citation for these things in a paper that Nina was a co-author on. The US Federal Trade Commission pointed out in that quote there that privacy is becoming an increasingly negative concern in the context of IoT. There was this blog post from a widely used blog about interesting things that talks about real evidence that people are starting to push back on IoT devices. And then I think it'll be lost at the bottom here. Roy Want wrote a very nice survey paper on, I think it was Roy and Trevor, right? Or is it Roy and Bill Shillett? I've forgotten the cause, but certainly Roy. And he highlights privacy and certainly security, but privacy is a very big concern. Okay, so many of you may know this book, Crossing the Chasm, right? And so the essential message of Crossing the Chasm is that any new technology essentially goes through a pretty standard pattern if it gets to the point of widespread adoption. And the point is, the early years are great. You get very enthusiastic early adoption, but then at some point you hit a big scary chasm. And for each technology, the nature of that chasm is different. And you have to figure out what is the chasm about. In the case of IoT, it's privacy. If you don't cross this chasm, you never get to the point of widespread adoption, et cetera, et cetera. So the feeling of loss of control is one of the key factors. So if you can give people comfort, genuine comfort that in fact they have real control, then we believe that there's an opportunity to overcome this chasm. And so the concept of a privacy mediator running on cloudlets is exactly what we think is the right thing. So here's the key design principles. If you are the owner of a sensor, and I'm waving my hands a bit here because, who exactly owns the sensor versus who exactly owns the data from the sensor, right? These are subtle distinctions that need to be sorted out. But if it's in your home data, you should have control over it. So the notion that they should be able to control its release is a very simple but very reasonable design principle. Interestingly, not all commercial entities accept that principle, right? If you're ever going to be able to actually implement that, you are going to need to have some infrastructure that is under your control on which this interception is done. And cloudlets emerge as the obvious point because they're dispersed infrastructure, they have isolation, they have compute capabilities for running things like video denaturing. And you could imagine these things being deployed, for example, one per home. It's an interesting question, who's going to manage it? You can imagine third parties who are entrusted. So if I'm tech savvy, may do the management myself, but most people may ask Verizon to do it for them or somebody else to do it for them and pay a monthly fee. So that's a separate, but they trust the entity that is running that, okay? So each census team is mediated by a piece of software that we call a privacy mediator, and it runs in the cloudlet. And the cloudlet is guaranteeing to you that this is a safe execution environment. And if this is compute intensive, you also have the advantage that you have the compute power right there. And if it's bandwidth intense, then you don't need to stream it all the way out to the cloud. You may be able to intercept it early, do the mediation, and perhaps only stream out a subset of the whole thing. So from all those angles, this is the approach that we see as a valuable approach. So pictorially, this is a hypothetical picture of how you might organize a cloudlet to do privacy mediation. So I have a cloudlet, and these are each virtual machines. Inside them, I may choose to have Docker or some second level of containerization if I want. But the important point is, these are thick walls of isolation and safety, okay? The raw sensor data from the zone, your home or your enterprise, comes in here. The appropriate privacy mediator filters the data, and then some suitably denatured sensor stream goes off to the IoT hub in the cloud. Now, here's the interesting thing. Storage is cheap, very cheap. I mean, I can buy 1 terabyte disk for less than $100 now at Amazon, okay? Netflix claims you should use a rule of thumb, 2 gigabytes per hour of video, encoded video. So 1 terabyte is many hours of video that you can buffer at full fidelity inside the cloudlet. Now, why might this be interesting? This might be interesting because one of the value propositions for sharing your data, sensor data in the cloud, is that they are able in the cloud to compare your data with that of others, to do big data analysis on it, all the things that you guys know well. You could imagine a request in the reverse direction of the following kind. Dear homeowner, comparing your water consumption, the denatured values that you're sending us, and knowing the size of your home, et cetera, and comparing it to your neighbors, we suspect there might be a leak, but we can't tell for sure. If you gave us the full fidelity data for some period of time, we could perhaps give you much greater confidence and maybe even pinpoint where the leak might be. So, you can then selectively choose to release that if you wish. The important point here is that in many cases, privacy questions that are asked in the abstract, people have no way how to answer them. This is like when you install an app on your Android smartphone or iOS phone. It says, I want to use a camera, I want to use this, I want to use this, yes or no. If you say no, the thing doesn't work very well. So you can only answer yes. And once you've answered it, you never ever have a chance to change your mind or to say, don't use the camera when I'm in this room or at this time of night or when I'm doing that. You never ever have that choice. So this kind of context-sensitive use is valuable. Okay, I want to now give you an example, a use case of a privacy mediator for denaturing live video. Okay, so the first step is you have to be able to do face recognition. You guys said Google have a great face recognition system, Facebook has a great one, but it's proprietary. I can't use it, right? You might be willing to run it as a service in the cloud, but you won't let me use it on a cloudlet. So we had no choice but to implement one ourselves. So what we did was well, I say we, that's being very generous. The person who implemented all this is one of my grad students, former grad students, Brandon Amos, who learned so much machine learning from doing this work that he fell in love with machine learning, is now a machine learning PhD student, okay? But the guy did a phenomenal job in the implementation. It is now used by so many people. It's on GitHub, so you just Google for OpenFace and you can find it. Basically, it includes this very important point, agile retraining on a cloudlet. So I'll show you a video which shows you that. The recognition is offloaded from the IoT device onto the cloudlet. So you could have a high-end GPU, things like that on the cloudlet. And the other thing it also lets you do is it allows you to export a model if you wanted to do the recognition on some device right there. Okay, so you can use it in any of these ways. Basically, what Brandon did was he very carefully studied the published papers of both the Facebook and the Google systems, which are named DeepFace 2014 and FaceNet last year. And based on the public description, figured out how to create OpenFace, and it's trained on a much smaller face database. We certainly don't have the sizes that you guys have. We combined two publicly available face databases to get 500,000 images, okay? But you'll see in the next slide, given this limitation, it does amazingly well. To the best of my knowledge, it is the most accurate face recognizer built on publicly available label data, as opposed to proprietary data. But basically what it does is we train a neural network, and what the neural network does is, for new faces, by passing it through the network, it comes up with a 128-element feature vector, which is a unique characterization of that face. And then that basically is I think of it as a SHA-1 hash for the face. There's a good, or SHA-256 hash. It's a unique characterization of that face in fixed length form. And then you can use something much simpler, and we use an SVM, support vector machine, to do simple comparison. If I have 10 people and you want to distinguish between them, this stuff works very well. So there's a tech report, citation is down there, you can get all the details. This is the Roc curve, which tells you how accurate it is. So the bottom here is, I believe, the bottom is false positives, and this is true positive. So the perfect detector would be a step function. The red curve came from DeepFace, which is the Facebook paper. They actually did human studies, and that red line represents human accuracy. The dotted line, which if you look very carefully, you can just barely see underneath the red, is their face recognition system. Now, unfortunately, the Google paper doesn't have an Roc curve that I can put, and I can't measure it myself since I don't have the code, so we assume it's at least as good as Facebook. Most likely it's much better, okay? So we'll just pretend that, but that means it's somewhere near the red line. The black line is OpenFace. Okay, so here's the easiest way to think about this. The area under the curve, the best value you can possibly have is 1.0, right? Humans are 0.995. DeepFace claims to be 0.997, superhuman. Okay, I don't know what FaceNet is, but OpenFace is about 0.973, which is, with about 1 to 2 orders of magnitude fewer training set size. I think that's very good, okay? So here's how we have built the privacy mediator. So you have incoming video. There's some decoding that is done. And there's a denaturing algorithm which receives an external denaturing policy. So in our implementation, it's very simple. We have the name of a person or a number of, this is person 1, person 2, person 3, or Nina, Pulkit, Max left already, etc. So, we use something simple like that. Interestingly, what we do is after we denature, we save the original bits. And I'll explain to you in a second why this is useful, okay? But you save it inside the VM, but we encrypt them. So the real face of the person is encrypted with a key, and that key is not used for long, and it's forgotten. There's an external entity that knows that key. So for example, in the Boston bomber case, if you had used a system like this and all the faces were denatured, under warrant, search warrant, you would actually need to see the real faces of the people. So when you have the appropriate permissions, we are able to reassemble and give back to the undenatured version of it, okay? Over here is the denatured video, which you would then feed to in parallel to any number of analytics algorithms. And you could also archive it. And so you could, by combining the archived denatured video with the encrypted original bits, you could actually reconstruct. If we have time, which we may not, I can tell you how we actually implement that. So the simple approach to implement this would simply involve first face detection per frame. You'd have to do this sequentially because it turns out all the implementations of face detection are sequential. There's not much parallelism because the faces can be at any scale. Okay, so if you want scale invariant face detection, it's unfortunately single-threaded code. Once you do that, the face recognition can be done in parallel. Each one can be recognized independently. So the minimum time for this is this plus the slowest of these. The bad news is that's too slow. Okay? The DLib implementation of face detection on a typical high-end desktop, which is kind of what you might think of as a decent cloudlet in a small environment, is over 100 milliseconds. And then a typical OpenFace execution takes of the order of 60 milliseconds on this hardware. So off the bat, 180 milliseconds with no further processing. For 30 frames a second, you only have 33 milliseconds budget. So this is a non-starter. So the critical insight is to recognize that even in athletic situations, at 30 frames a second, faces don't move too much between frames. So what we do is we use the much cheaper, computationally cheaper, object tracking, face tracking, once we have found the face. Okay? So that turns out to be much cheaper, only 11 milliseconds per face, and that's faster than the 33 milliseconds. Okay, and you can do it in parallel because if I have multiple cores, I have multiple faces, I can track each one of them separately. I won't have time to go into this, but there's an additional optimization which we describe in a paper we've just submitted, which is called perceptual hashing, which is one more order of magnitude faster. So this is a weak comparison. So it'll never say two faces are the same when they really are not, but the opposite might be true. There's sometimes when it says it's not the same face, when in fact it's the same face. But you can think of it, it's almost like, I'm trying to think of the term we use in long ago in undergraduate compiler. I mean, you learned the concept of strength reduction, right? Replacing expensive operations with cheaper operations. That's basically what's going on here. So unfortunately, the net effect is that you end up with a much more complicated system. So you have the input video stream. As soon as you get the frame, you send it to the tracker to start finding the faces and doing this. But you do one thing. You realize that either because of a drift or because a person's face was not even detected, so you're not going to be able to recognize it, you might have missed a face. So we hold on to the face for a little while, in fact, for 1 second. So there's actually 30 frames here. If from the face detection and recognition side, we, in one of the later frames, discover a face. We go back and track backwards to find the faces that you might have missed because your face detector was not good enough, okay? And then you can denature it. And this turns out to be a very, very good approach. So let me show you one video, and then I will have to wrap up pretty soon. I think after that.
RT-Face is a real-time face denaturing system that protects users' privacy. It denatures faces in real time using object tracking, face detection, and recognition. For an unknown person in a camera feed, it blurs that person's face by default. When a user wants his face to be shown, the user trains his face first and then specifies his privacy policy to RT-Face.
So it's just a few seconds of video capture. That's all we need for the training. So now he has checked the box that says show face.
Once RT-Face recognizes the face to be shown, it stops denaturing for that particular face. RT-Face uses deep neural network-based face recognition to achieve high accuracy. It also leverages fast object tracking to run in real time.
Okay, so it's pretty fast, and training new faces is really, really quite easy. Come on. Okay, just as a footnote here, there's some measurements. It's a long story, but the tracking accuracy turns out to be very, very good. It's a short message of the slide. Stuff about privacy leaks. I'll skip the part about exactly how we do the policy-directed reversal. And here's the conclusion, that live video is a powerful sensing modality for IoT. I think this is important to appreciate. The problem is privacy is, even without video, is already a big concern, and the video just makes it worse. And the key observation of this work is that denaturing can potentially allay privacy concerns, and then we can actually do it on live video, not just batch-oriented processing. Okay, that's basically all I had. Happy to take questions. Yeah.
What would you see as kind of fair, because you highlighted many applications, right?
Yeah.
But if I want to use this for inside my home, then it's easy to get my family members to have their faces trained.
Yep.
Using the previous example.
Yep.
And visitors that would know what to cover or not. And then recently in the media, right, it was talking about should Airbnb guests be allowed to turn off your Nest Cam if they're Airbnb in your place? It's privacy for one, but it's security for the other. How do you see this? How do you see that opting in and out when you have so many different settings?
Yeah.
If I want to do it at a mall versus at a place where I'm family living.
Yeah, I think this is a very good question. Let me be upfront and straight about this and say I focused on the mechanism. Using policy only to give me some intuitive guidance about what things might be need to implement. Okay, I think those Airbnb kind of situations are tricky situations. I suspect at the end of the day, there's a significant cultural component in it. And by cultural, I just don't mean like countries' culture, but it also different companies have different cultures, different communities have different cultures. So whether it is a policy that is sort of mutually created with the community, or is kind of inferred, I don't have a good answer on that. I think more work is needed by people who are good at that kind of stuff. I'm not, I don't have the skill set for that. But I would love, if you guys are, if you guys have people like that, like I guess ethnographer kind of people, right? The kind of social researchers. Those are the people who would would do that. But what this is saying is, you tell us what's right, and we can actually make it work, and that's the key. Yeah.
If you're talking about the security camera scenario where you can't expect people to come in and train their faces,
Yep.
for instance. So in that case, are you also focusing on automatically finding the screen?
This is actually beautiful because there's a person, Norman Sade, who's also at Carnegie Mellon, who's actually, when he saw this demo, the live version of the video that I showed you, said, oh, this is cool. We should be able to do something together. And so here's the idea. OpenFace, as I told you, essentially spits out a unique 128 element feature vector. It's a bag of bits. So I could imagine, just like I send people my public key, I could send them a feature vector for my face. And you could imagine a process by which you could almost imagine, here's my face. Dear video cameras anywhere in the world, here are the rules I want you to follow. Now, where should you send them? Is there a global registry somewhere? There's some questions about exactly how you do it, but the general notion that a person, my face, is like my public key. In fact, it's not such a bad idea, to think about that.
I just want to ask, before we have just 3 minutes left, is there anybody online who wants to ask a question? Well, can they be together, Sarah? Yeah.
They may not have known that.
Okay, do you want to just wave your hands if you want to speak up, otherwise we'll keep chatting over here.
So if anyone remotely wants to ask a question, raise your hand or wave, because we can't hear you.
Yeah.
Okay, yeah.
So when you start thinking about sensor fusion within a home, now we have video and audio.
Yep.
Sensors that
So just footnote, and thank you for mentioning audio. There's a class project in progress, final demo on December 6th, to take exactly what I showed you and apply it to audio. So imagine sensitive words like a password or credit card number or something like that, recognizing it in the audio stream and denaturing it. Okay, sorry, go ahead.
I'm just going to ask, there's going to be more and more sensors in the home.
Yes.
Or in public
Yeah.
locations, and that the power comes into fusion of
Yes,
data.
yes.
And so you're going to take all these different sensors, be able to denature it. So with that comes more computing, more being able to.
Why do you think Intel loves cloudlets?
So do you think that's the direction? That we
I think so.
Okay.
I think having powerful compute close to, at least concentrated in a given trust zone, like a home or an enterprise of some kind, and doing the denaturing right there is the way to go. That's the only way people are going to have any confidence in the privacy. If you say, send it to the cloud and then we'll do it for you, people just don't buy it, right? I mean, you may mean well, but there have been so many leaks of passwords and credit card numbers and privacy information that people say, look, you are making promises you cannot deliver on. And so a better approach is to say, somewhere close to me at smaller scale, I'll take care of it, and I'll send you the denatured version.
I mean, I had a bit of concern about the security of the cloud as well.
Indeed, the physical security of the cloudlet.
So yeah, because our data centers, Google
Yes.
employs people who actually
Yeah,
control
so
the physical
that
security.
is fundamental to decentralized computing. I mean, your desktop at home has that property today, right? Physical security of your home environment is something you treasure, hopefully. So the short answer to your question is yes. My belief is as cloudlets get more widely deployed, there's a business opportunity for companies like Dell or HP, they make these boxes, to make them in ways that are maybe tamper evident, maybe making anything totally tamper resistant doesn't exist, but tamper evident might be possible. Like all security things of this kind, it's a question of how high a bar do you want. With enough cost and enough effort, you can raise the work factor very high. But at the end of the day, it's got to be, the lock has to be worth the thing that it's protecting. So
I mean, I guess in terms of security, like if this data is being collected on the cloud, there's the possibility that somebody actually hacks into the cloud, cracks into the cloud and steals data. But here, the threat from malware, etc., is still there.
Yes.
Which I mean is more persistent than IoT based in IoT based.
But let me tell you a little fact of life. People are amazingly forgiving of themselves.
That's
Okay? So if Google loses their data, they're mad. If they lose their own data, oh well, too bad. Right? So I think one of the things that happens when you shrink the scale and sort of localize it a little bit more is somehow there is greater tolerance for imperfection. It has nothing technical about it. It's purely, I think, human characteristic.
All right. Thank you so much, Satya.
My pleasure.